Hey there everybody. We're going to be working with trigonometric identities for one last video, and we're going to be proving trigonometric identities are true within this video. Now, you'll recall that an identity is an equation that's true for all values of its variables, and I'm going to show you how to basically prove that certain expressions have to always be equal to one another no matter what. Alright, now often people get confused with the difference between proving an identity and solving an equation. And so I've got an example of each on the screen right here, and I want to explain to you what you're trying to accomplish with each and what the essential difference is. I want to look at the expressions on either side of the equal sign. You do see how they are both equations. An identity is an equation, and so is an equation obviously. So they look similar. The difference is this. If you check out the expressions on either side of an equation that you're trying to solve for, if you're asked to solve for the equation, those expressions are only sometimes equal. Side note, you might remember that an equation that is equal for only some of its values is called a conditional equation, and that's pretty much what you're asked to solve, are conditional equations. And that particular equation, very simple one based on what we've been studying in this chapter, would give you two solutions, 30 degrees and 210 degrees. Because those are the only two angles between 0 and 360 degrees that have a tangent that's equal to the square root of 3 over 3. Alright, now with an identity, if you look at the expressions on either side, those expressions are going to be equal for all values of theta. Meaning regardless of whether theta is measured in degrees or radians, and regardless of the actual angle measure that you plug in, as long as each expression is defined, this is going to be a true statement. So it doesn't matter whether I plug in 30 degrees, 45 degrees, 120 degrees, everything would make this equation true. Now, that's something that you have to be able to prove, and that is, again, the goal for this video is for you to be able to prove an identity. Now, let me go through this one really quickly so you've seen how to prove an identity before we really talk about the techniques involved. And the way I'm going to do this is I'm just going to take one side of the equation, either this expression or this expression. I'm going to take the one on the left side, and you use algebraic techniques, substitution, whatever works really, in order to transform that expression into the one that we're saying it's always equal to. Alright, in this case we're going to use substitution. Now we're trying to change this from an expression that has a sine squared of theta into an expression that has a cosine squared of theta. So we need to think about, is there any relationship we know between the two? And we know an identity, right? Sine squared theta plus cosine squared theta equals 1. I'm going to use a variation of that. I'm going to replace sine squared theta with 1 minus cosine squared theta. Alright, so those two expressions that I highlighted are equal to one another. And then it's just one more step to go ahead and prove that the original expression was equal to 2 minus cosine squared theta, because there's no distribution to do with the parentheses, because that would just be a positive 1. I can just go ahead and say 1 plus 1 is 2, and then I've got minus cosine squared theta. There you go. So proving an identity is proving that two expressions are equal to one another regardless of the values of the variables that you might plug in. Now let's go through and do some examples together, a few more. One of the things that's going to happen with identities is they're going to look difficult to you a lot of times, and certainly the expression that you see on the left side of this equation looks difficult. Now here's the way you're going to go about trying to prove the identity. You're first going to try to identify which of the expressions in the equation looks more complicated. Now clearly this whole quotient of differences is a little more complicated than 1. And so what I'm going to do is I'm going to write down the more complicated of the two expressions again. And then what we're going to do is we're going to try to think about what algebra techniques or what substitutions can we use in order to get that complicated expression to look like the simple one. Now, it looks preposterous to say that the something to the fourth power minus something else to the fourth power would equal the same, would be the same thing as the difference of the squares of those same values, right? Sine of the fourth of x minus cosine of the fourth of x, you wouldn't think is equal to sine squared of x minus cosine squared of x. Why am I talking about them being equal? Because the only way you divide two expressions and you get a 1 is if you divide equal expressions, right? So there is some way that this numerator is actually equal to this denominator? Well, the technique that we're going to use here is going to be an algebraic one. I'm going to use factoring to show that that expression is going to be equal to 1. Both the numerator and the denominator fit a difference of squares pattern. Obviously, this is a perfect square minus a perfect square, but the numerator is also a perfect square minus a perfect square. And I'm going to start by factoring the numerator. Remember, you factor a difference of squares into conjugate pairs. And so sine fourth x minus cosine to the fourth power of x is going to be the same as sine squared x minus cosine squared x times sine squared x plus cosine squared x. I'll write that down. And then we could do some factoring with the denominator, but for the moment I'm going to hold off on that and I'm just going to rewrite it. Now, factoring is a very common technique whenever you're trying to prove identities because often it achieves results like what you're going to see right here. When I wrote the numerator in factored form, the numerator and denominator have a common factor now, sine squared x minus cosine squared x. And so what we can do is we can cancel those common factors. Those will both become 1. And so now that very complicated expression is a much simpler looking sine squared x plus cosine squared x. Make sense? And then sine squared x plus cosine squared x is an identity that we know. That's always equal to 1. So there's the substitution that we made. All right, so again, using algebraic techniques and substitutions, we're able to prove that no matter what the value of x is, that this big expression here is always going to be equal to 1. Pretty cool, right? It's like a puzzle. I really love this kind of stuff. Let's try another. All right. This time we're going to show that the sine squared of an angle theta is always equal to 1/2 times 1 minus cosine of 2 theta. We again need to pick out the more complicated of the two sides, and in this case I kind of think the right side of the equation is more complicated because here you're just squaring the sine of an angle. Here you've got a double angle, you've got a subtraction problem, and you've got a multiplication problem. A lot more going on there. So I'm going to copy down the more complicated side. Now what we need to do is consider what are the trig ratios in the expression that we're working with and what do they need to become. You see we've got the cosine of 2 theta and we need that to become a sine squared of theta. So let's think about the identities that we know and how do you relate a cosine of 2 theta with a sine squared of theta. Hope you've got an identity in mind. We're about to make a substitution right here. We're going to substitute cosine of 2 theta and we're going to replace it with 1 minus 2 sine squared theta. Now that's a pretty good start. You can see we were able to make the cosine of 2 theta into a sine squared of theta, which is what we want to get on the other side of the equation. Now let's just go ahead and simplify that expression. I'm going to use distributive property, but not with the 1/2 like you might think. Let's hold on to that. And let's work inside of the braces. Let's leave this 1 alone. I need to distribute this negative sign. So that'll give me a minus 1 and a plus 2 sine squared theta. All right, then continue simplifying. You can tell we've got a 1 minus 1 inside the braces, and so that's going to cancel. It's going to be 0. And we're really just left then with 2 sine squared theta. And if you multiply 1/2 with 2 sine squared theta, that's going to give you sine squared theta, right? All right, another successful proof, and we're able to show that this expression is always equal to this expression, no matter what the value of theta is. We're going to do one more example in the video. Here we're going to show that the square of cosine theta plus sine theta has to be equal to 1 plus the sine of 2 theta. Again, let's pick the more complicated of the two sides, and I would say the left side in this expression, in this equation, is going to be more complicated than the right side is. So I'm going to copy that down. We'll start there. Now we'd like to take this expression with a cosine and a sine and ultimately make it into a sine of 2 theta, but there's nothing we can do immediately with a cosine of theta plus a sine theta to make that happen. So let's just go ahead and use some algebra and square that binomial. Use our a squared plus 2ab plus b squared pattern, and that'll give us cosine squared theta plus 2 sine theta, or cosine theta sine theta I should say, plus sine squared theta. Now to this point this might not look like a simpler expression, but there's two great things that are at work here. We have to be able to get a 1 somehow, and we have to be able to get a sine of 2 theta somehow. Well, the 1 is going to come from the fact that we have a cosine squared theta plus a sine squared theta. And that is equal to 1, correct? So let's do that substitution now. All right, so what I've highlighted, you can see what I substituted in its place. Now we just got to work on getting the sine of 2 theta. And you might remember that the sine of 2 theta is just equal to 2 sine theta cosine theta. Well, 2 cosine theta sine theta is the same thing. So here's our next substitution. We're going to replace 2 cosine theta sine theta with sine of 2 theta. All right, there you go. You now know what it means to prove an identity. You're showing that two expressions are equal no matter what the values of the variables in the equation are. And you've learned some algebraic and substitution techniques in order to help you with those proofs. All right, guys, thanks for watching. See ya.